All right, welcome to the Mr. Maze Power Hour. Don't forget to smash that like button and annihilate that subscribe clicker. Beat the garbage out of that bell so that you know when with new notifications when new videos are coming out. If you could go ahead and pause the video, take a look at these A through G FRQ tips for the AP questions, also for FRQ questions in my class, like the ones you will find on the upcoming little mini quiz we got. So go ahead and pause the video, jot these down. All right, I hope that was to your liking. I tried to be very explanatory with these A through G tips. These are the same ones I gave you in class, but if any of them don't make sense, you'll notice actually for number D, I forgot to put a space between CSOCs and 4. But it would be just too much work to go in and put that space and do another screenshot because I'm a piece of garbage. No, I'm just kidding. But with that all in mind, I hope this all makes sense. If it doesn't, come find me during office hours or a free period, and I got you covered. All right. As I have explained in class, and now I'm going in more detail with right now, we are talking specifically about quantitative data right now. Why did it use the pen? I wanted it to use the highlighter. Here we go. We are speaking specifically about quantitative data and using CSOCs for quantitative data. Always use CSOCs. You know what the elements are of CSOCs. They are center, shape, outliers. Oh my goodness, context, shape, outliers, center, and spread. You can tell, I always say I'm not a big fan of acronyms, but if it works for you, it works for you, and that makes me very, very happy. So we have center, shape. I hope you have it just nailed into your brain, outliers, along with my disgusting handwriting that you can remember. Oh my goodness, I did it again, guys. Am I not a legend at this? Okay, let's try again. It is context. Oh, save me. Context, shape, outliers, center, and spread. Maybe for me, context will be the second to last one. Okay. Now, as you might remember, I did a first set of notes. I would recommend listening to that first set of video notes because I go through all the elements of CSOCs. Not as thoroughly as I will in this video, but I go through the sort of basic components and I skip a few of those in this video. So I would recommend listening to that first video as well to make sure you're comfortable. I'm going to slide over from CSOCs real quick because when doing your FRQs, you'll either have a describe question or you'll have a compare question. For describe questions, you're normally looking at one particular graph. You must use numbers. If you're not sure exactly where the number's at, be sure to use about or around. And then, of course, do use CSOCs, okay, when describing the graph. Then, if you do a compare question, you actually, as I've said in class, don't need to use numbers. I like to use numbers. You will not be penalized if you use numbers, but again, just remember around and about, things that approximate it, unless it's very obvious. Like if the data point is 4.0, don't say around 4.0. If the data point is that, say it's 4.0. But again, be sure that it's something that you can say with certainty. As per the earlier point, I think it was literally point A. Don't give incorrect information on an FRQ. And with compare, I said this above, but compare everything. Every graph, every component of the graph, and use, of course, our favorite CSOCs once again. And that's the cool thing about statistics is this sort of CSOCs method works perfectly for every question. You just have to be sure to use it effectively and understand how you're going about it. Okay. And the two things I want to warn you about, these will be our sort of big, keep this in mind thing. One of them is be sure to go back to previous data if it's used again. So, and I will give you the old wink, wink, hint, hint. This occurs in your mini quiz. When I say go back in previous data, what I mean is you might have a question with multiple parts, like question 1, but then it's A, B, C, and D. And when you're looking at those multiple parts, you might be asking, well, why am I messing around with these subsections? Why would I ever go back? Well, you might find in question D that you're doing CSOCs on a box plot, right? And you're calculating outliers, which we've said we're going to learn how to do in this video, okay? And, well, actually, I don't know if I said that, but now you know we're going to do that in this video. And we did it in class, so actually you should know the hint, right? And you might find that, the maximum does represent an outlier, right? You're like, oh, this value up here, there's got to be an outlier sitting somewhere up there, because it turns out from our calculation that the maximum is too high for our calculation of outliers, and therefore there have to be some outliers, which you'll remember on box plots, we do outliers as these little stars, right? So that would be an outlier, that would be an outlier, that would be an outlier. But you may find that this maximum has to be an outlier, and the maximum actually has to be lower because we've calculated it, right? And if you find that to be the case, you can't just say that that maximum is the outlier. There may be multiple outliers here. And if you go back to a previous question, there might be a data set that's used, or a histogram with a data set, or a dot plot, and a dot plot would have the specific values. And the AP exam and I expect you to use those previous answers to inform your new responses. Now, if I ask you, what does this box plot show? Don't give me information from a previous graph that can be shown. But if you say it shows that there are outliers, those outliers are at blah, 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 do use previous data to determine that, if that makes sense. I guess to be very clear, what I mean is, don't say that the box plot shows that it's like bimodal. As you know, box plots cannot do that from the above parts that I showed you. But that's what I'm saying. So make sure you don't give credit to a plot that can't show that thing, but do use previous data to inform your data set. Okay, it's a really good thing to keep at the front of your mind. Okay. Let's roll. You should know context. We went through context. You should feel very comfortable with context. I really am not going to go into too much detail. You can be, just be clear what the context is of your situation. What's going on, right? And what's measured. Okay. Moving on to shape. Now, we went into some pretty in-depth notes in the first class period on shape, but let's go through this really quickly. You must understand left skew versus right skew. Oh, that was a terrible looking right skew. It's not my best work. Actually, let me show you approximately normal, right? Let's do that. So this is normal. We would say approximately normal because it's probably not perfectly normal. Approximately normal, we would say. And this would be left skew. And then, of course, this would be right skew. Okay. Something we went over in class that I was really excited to show you. For all of these, the mode is the highest. Right? We know that to be the case. However, we did note a few interesting things. In a left-skewed graph, right? Everybody's favorite, the left-skewed graph. We want to know what happens with a left-skewed graph when it comes to the mean and the median. And in a left-skewed graph, the median, we agreed, which I'll make green here, the median, is actually higher than the mean is. And the reason for that is we have this delicious tail sitting here on the left, and that tail is pulling our average down. And remember, the mean is the average. So the mean, and we said this in class, but remember, the mean is like a gentle flower. Oh, so gentle. The mean is demure, shy, careful. And if you add extra values to one side, that will pull your mean. It will dramatically impact your mean. On the other hand, it's not going to dramatically impact your sweet median, who is, as we like to say, robust. The median's tough. It stays there because when we cancel out values, it won't matter too much how much was going on slightly to the left, because as we cancel those values and get closer to the median will only shift slightly. And so therefore, of course, you will understand similarly that the median is going to be further to the left than the mean in a right-skewed distribution. And because the left is always low values and up is high values, that will mean that for right skew, it is the mean that is greater than the median. And then for approximately normal, all three values sit the same. MMMs When my sister was a kid, she used to call them MMMs instead of M&Ms. And that's why. It's because she understood the value of statistics, the mean, the median, and the mode being the same in an approximately normal graph. All right, this is, looks like I'm a child that just puked up a bunch of Play-Doh I ate, but hopefully it makes good sense to you. What you should take away from this is that the mean is a very gentle thing. The median is more robust. When we get a left-skewed distribution, the median will often be a higher value than the mean. In fact, always be a higher value than the mean, as the mean is getting pulled down by lower values. On the other hand, from a right-skewed graph, it is the mean that will be higher than the median because the median will stay closer to the normal, but the mean will get tugged further up to higher values. Remember that with approximately normal values, we find that they are all the same, the mean, the median, and the mode. And do keep in mind, I mentioned this in class, if you're wondering about skew and you have a weird graph where your x-axis is for some reason on the y, right? Your variable that you're measuring is up here where it should be. Remember that up here is lower values, right? The further left you go, that's the lower values, right? Okay. So keep that in mind normally. That's how they like to go about it. Although sometimes, and I will say this too, just because I think it's worth stating, right? Lower values are the left for your skew. So if they do a terrible graph like this, where they put your beautiful x categorical variable or quantitative variable, of course it'll be quantitative for this. So actually, I take that back. If they take your x quantitative variable and they go up like this, 1, 2, 3, 4, and this is not frequency, this is like actually the thing you're measuring, and frequency is here for some reason, right? Then remember this is the left side of your distribution and this is the right side. So it will vary plot to plot, but the one that I believe I gave you before as your like hard and fast rule in class is just that low part of the distribution is the left, right? When you actually have it in a distribution set up to be the left side, right, correctly, left is low. Left is low values, right is high values. All right, we're rolling. So we've got those metrics sitting there, and we're good on the mean. And remember that the median is often called the middle. This is going to seem obvious for many of you, but keep that in mind because often when you describe stuff, you're going to want to say the middle of the distribution is at blah or near blah, right? You can say median too, but just be aware that that's the situation. Okay. You will also remember that when we are, well, actually that's spread, so we'll hold on that for now. Let's go a little bit further into shape, shall we? We talked in class about this. We talked about unimodal versus bimodal versus multimodal. Okay, those should all make sense to you. Actually, let me make my bimodal one look a little more bimodal, right? Cool. So this is unimodal. I'm going to go just really quickly. I know we have this in the other notes. Bimodal and multimodal. Again, you should see there are multiple peaks for the multimodal. On the other hand, there are only 2 distinct peaks for the bimodal. And then we have the single distinct peak for unimodal. We had a really, really cool discussion in class. I brought this up on purpose because sometimes it happens on the AP exam where like if you have like a histogram and we said like if you have a really high peak here and then a slight dip and then we go up to another high peak and we have this sort of thing going on, we would say this is unimodal. Wisely, one of my students said, if you squint really hard and let your eyes get blurry, you can tell it's just a single mode there. And the reason why is the rule I like to use, and this is not a hard and fast rule, but the rule I like to use is you will note here, even though there are 2 peaks, you will note that the dip that we have never goes down to the dip to the left of that bar that we count as our peak. So we count this as all one peak because it never really settles and then rises again, if you will. There's an argument to be made for bimodality here, but it's not a good argument. This is definitely a unimodal distribution that's just a little bit oddly framed. Okay, so that should make good sense to you. And we understand multimodal, that makes sense. Bimodal makes sense. So we are rocking and rolling. I brought this up in the first video, but again, it is considered a cluster if you are missing like bins in a histogram, and this is considered a gap, so if I have this going. So remember, we have to, and this is something, I think I brought it up earlier when we were doing like the notes for AP, but can use every bin. Put bins in there, make them equidistant. You can start wherever you like on the x-axis, but you must put bins for the spots between, even if there are no data points there. This is considered a gap. These are considered clusters, and that should feel very comfortable. All right, we're doing well. This video is not too long yet. I'm not too terrified, but we'll see. Again, this should be a review from video 1, but remember, roughly uniform. These are all around the same size, so we would say that this is a roughly uniform distribution. And remember, on a box plot, we cannot be talking about normality ever or modality ever. If we were looking at a box plot, we would just say symmetrical, that the data is symmetrical. And really quickly, I want to go through that. On a box plot, if we said the data was symmetrical, we would be saying like this would be a symmetrical box plot for the most part, roughly symmetrical, right? Versus a left skew box plot, right? This would be a left skewed box plot, and then a right skewed box plot would look, as you could imagine, like this, to a degree, right? And I'm bringing this up just because when we come up to symmetry, that's normally when you're going to say it's a symmetrical distribution, right, for a box plot. But popping back over, other ways that symmetry is used with different kinds of plots is we say, right, a roughly uniform distribution is symmetrical. So we can say it's roughly uniform and symmetrical. And then another one is approximately normal, which again, you cannot tell with a box plot, but if it is like a histogram or a dot plot or a stem plot, we can say when something is roughly or approximately normal, and that is considered symmetrical as well. All right, we're rocking and rolling. We talked about our mean and median. Really quickly, I want to make sure that you totally and in every way understand how to calculate the median. This was a review from class as well, but just be aware. The median works when we put a bunch of data points in order and we have to figure out the center number. If there is an even number of values, let's say it's 1, 3, 5, and 7, we take the middle two numbers once we put them in order, and we average them to get 4, and that is our median. If we, on the other hand, have an odd set of numbers, 1, 3, 5, 7, and 9, we cross out once they're in order, of course, and the middle number 5, that's supposed to be a 5 if you can believe that, is going to be our median. So that should feel very, very good. And we're rocking and rolling. All right, I'm really proud of us all. We're doing a really good job. Now, some things to bring up. Remember, and I brought this, this is apparent from the list of rules up at the top for FRQ questions. But remember, I showed you a question class where we had a histogram, and I asked you, hey, what would be the median wait time in minutes? And I told you, remember to calculate the median wait time. Don't presume in a histogram that each bin are not evenly distributed. Don't assume they are evenly distributed. With data. What do I mean by that? Well, I say they're not evenly distributed with data because even though the frequency will be here, let's say this is 6, 5, 4, and so on going down to 0, always going from 0 up for the frequency, even though we know that there are 6 data points here, we don't know where those 6 data points are. And so wisely, what we were able to say was, you can't for sure compare the following. You can't compare exact ranges, means, or medians when it comes to histograms. Because even if it looks like the range is exactly the same between two histogram models, we don't know if the data points are actually distributed evenly across them, right? So the actual range might be different. Same with means, same with medians. So keep that in mind. The only thing we can be sure is of with histograms in the example we did was with standard deviation, which we're only going to go into a little bit in this video. We could tell if standard deviation was greater or less than. Okay, so I'm going to go through that really quickly. You should remember this all from our notes, but we looked at some graphs. And actually, I'm going to use some dot plots because those are the easiest, right? And we looked at a few dot plots, and I said to you, this is an example of a dot plot right here with a high standard deviation. And on the other hand, this is an example of a dot plot with a very low standard deviation. And that should make good sense because the standard deviation is a sort of universal marker that determines where certain amounts or certain percentages of the data is going to fall, right? So within one standard deviation of the mean, remember standard deviation always belongs with the mean, never with the median. Within one standard deviation of the mean, we need 68% of our data to sit there. Always, 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 right? And again, we go into further detail moving forward on that, but we need that to be the case. So the closer together our data is to its mean, the average, the smaller the standard deviation because the less space you have to travel from one side to the other to get 68% of your data. On the other hand, for this upper graph, our mean, if you were to average these 3 points and these 3 points, would be somewhere around here. And so the amount of space you would need to actually stretch a standard deviation one way to the other to get a full breadth, don't think that's a box plot, by the way. This is just standard deviation markers I'm stating. 1 and 1, right? With this being our mean, right? Because, oh my goodness, that's hideous. With this being our mean, because it's the average of those points, it would be a much higher value. And that should make good sense to you as a conceptual concept. Please do be sure to find me if that doesn't make sense. Again, conceptually. I said a conceptual concept. Conceptually, if you will. Okay. I brought up range momentarily as we were zooming through. You can see, I hope, I know this is a bit erratic the way I'm weaving around these concepts, but I hope you're starting to see how I'm already now going to bring range down, if you will. I talked about ranges up here, but all of these concepts interweave. Okay. Remember that the range is high minus low, I should say. High minus low. And two things that we noted in class about the range are that if I say the range is, and I ask you to fill that in, right? If you're supposed to say the range is, you give the value of high value minus low. So let's say my range is 1 to 5. For the range is, I'm expecting you to plug in 4, right? Because 5 minus 1 equals 4. Okay. On the other hand, totally different, if I say the distribution, or if the question says the distribution, or if you in your answer say the distribution ranges or varies, right? Either from, now you got to give a span, excuse me, from 1 to 5 is what you would say there, right? So you'd give your values there. And that's just a phrasing thing. Okay. I do really quickly want to step backward and just remind you, when we're talking about means and standard deviation, I said means and standard deviation belong together. Remember that we have two clumps. We have mean and standard deviation, right? And those are when you have no skew and no outliers. Why? As we said, for both mean and standard deviation, they are gentle flowers. Gentle flowers that are highly affected by extreme numbers that will destroy them and hurt their feelings. And remember that standard deviation has this cool sigma that is its way of being presented. I also do it like this, like the sort of O from French, although it's technically not that. It's this like sigma thing, whichever way you want to put it, right? And again, a side note, you won't need this for the quiz necessarily, but variance is just the standard deviation squared, right? Okay. But all of those sit together, mean, all that. And on the other hand, if you do have skew, right, and you do have outliers, if any of those are a problem, then you're going to work with, oh no, I did the highlighted thing again. Let's try it again. All right. Then you're going to work with the median and the 5-number spread. Or 5-figure spread. Both are phrases that you might use. And the 5-figure spread is as follows. It is a minimum, a first quartile, that's a 1, a median, aka the second quartile, a third quartile, and then a maximum. And that, my brilliant students, is your 5-figure spread or 5-number spread. And that's going to be your magic box when you're working with center for medians. So we have our 2 boxes. So when we're talking about center and CSOCs, these are the boxes we will roll with. Okay, we've covered shape, we've covered context, and we've covered center very, very well. I want to take a little time for outliers really quickly, and this is a good transition point because we've just talked about the median, and what better way to talk about finding outliers than to look at finding outliers for a box plot. Again, this is a reminder from class, but let's roll forward and take a look. Let me do purple for this. Let's do purple. Actually, you know what? You know my favorite color is orange. Let's mess with orange. Here's my orange box plot. Let's both make a box plot and let's talk magic with that box plot. So the data I had in class was something like this, I believe. Actually, I know it was this. It's actually exactly this. I'm doing that coy thing where I'm like, I think it might have been, but it was these numbers. So we have this data set. And I want you to imagine I say, okay, go ahead and make a box plot of this. Now be aware sometimes, as perhaps with my quiz, I will literally give you quartile 1, median, quartile 3, min and max. And I might give you some other values like mean and standard deviation, and you should know that you shouldn't be using those with a box plot. Big alert. Mean, standard deviation, like we said, these are measures of center that do not go with a box plot. They do not roll that way. They don't know each other. They don't sit together at lunch. Okay. We have our data spread. Let's go ahead, let's make a box plot. Okay, a frequency box plot. Or not a frequency box plot, a value box plot. Okay, we're taking a look at these numbers. We're going to find our median. Let's do it nice and easy. No, 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 no. Oh, goodness. No, no. And we have to find the average of these 2 values, which should bring us to about 26. Okay, we've canceled 3 on either side, and then our middle number is 26. So that's our median, aka our second quartile. Now we're going to take a look at the left side of the data. And again, we go no, no, and we find the average. And our quartile 1 value is going to be the average of these 2 values, which is 21.5. And then we'll do our upper quartile. And we'll see that if we take that, no, no, the average of these 2 values will be quartile 3. And that is 33. Easy as can be. Now we're going to do max and min. This is our max. It's the highest number. This is our min. It's the lowest number. And suddenly we do the following. We take our min. We put it there. That's our minimum, 16. We draw our line. We put our quartile 1 here, which is 21.5. Then we have our median. I would actually have a plot below this, right, where everything's equidistant. I'm just being lazy right now. I was lazy in class too. I'm very lazy. This will be our median, which we said was 26. Then we go to our third quartile, which is 33. And then our maximum, which actually, if you think about it, would be way the heck out here, 73. And that's our max. Okay, we're rocking and rolling. We've made our first box plot. Congrats to us. This is where I teach you that interquartile range thing, which we talked about in class. So IQR is super important for determining if you have an outlier or don't. Wisely in class, someone said 73 has to be an outlier. So what do? Well, we find our interquartile range. That is equal to quartile 3 minus quartile 1. Remember, by the way, side note, that quartiles split up the data into 25% chunks. Right, so min to quartile 1 is 25. Quartile 1 to median is 25. Median to quartile 3 is 25. Quartile 3 to maximum is 25. This is why we can't tell modality or normalcy or any of that from a box plot. We can just tell where, half our data points sit, the other half, the middle, this, that, and the other. And the interquartile range is super important, right? Because that helps us determine where 50% of our data, in fact, the most important 50% of our data, the 50% of our data on either side of the median, the center, sits. And the equation goes as follows. You do, for your maximum, I'm doing it again. He's at it again. Quartile 3 plus 1.5 times the interquartile range. Okay. And whatever value you get, you'll get a number, right? If that number that you get is smaller than your maximum, then you have outliers. Actually, any value greater than this any value greater than your third quartile added to 1.5 times your interquartile range is an outlier. I just said outlier. Is an outlier. Similarly, if you take your first quartile and from that you subtract 1.5 times the interquartile range, and this is all review from class, this should all stick with you, that will give you another number. And any number that is, by definition, right, any number that is lower than that number, right, is going to be an outlier. Okay? So if you have, and actually I want to make sure this is clear because I'm seeing from the up top, I've put the same signs that it kind of mushes itself together. So if you have taking you're looking at your mins, right? And you calculate your first quartile minus 1.5 times your interquartile range, this situation here, you're going to get a number. That number is the lowest value that can be a minimum, right? Lowest, that's what I want you to think of it as. Lowest value that is allowed to be your minimum. In this case, minimum. And in this case, maximum. So quartile 1 minus 1.5 times the interquartile range, that's the value that's the lowest value you could have that's still your minimum. Anything lower than that value must be an outlier. Maximum, if you take your third quartile and add 1.5 times the interquartile range to it, any value bigger than that, any value that is greater than that number, must be an outlier because that is the highest value that is allowed to be a maximum. And then you must be sure, because on a box plot, you'll have your box, you'll determine that 73 is an outlier, so you'll put a star for 73. And then you'll find your next highest point that is not higher than your upper quartile measurement. And that will be where your new maximum sits. In this case, actually, it's at 33. So remember that for a box plot, if your max sits there, you don't actually draw anything there. So it would look something like this. Okay, but make sure to do these calculations and make sure we said this earlier, but make sure you check previous data sets to see if there are other values below this point that count as outliers. Because there might be in the actual data set. Remember that the box plot won't show that, but you should look for that situation. Okay, very complicated, but I hope that made good sense, and we're rolling through. Okay, we've done all these quartile measurements. We've talked about standard deviation. You will see on Canvas that there are two pictures of the calculations you can do to find variance, standard deviation, mean and median and quartiles. On your calculator, your TI-84, please do be sure to check that. And we talked about how standard deviation separates, but that you can't tell the mean, median, or range of a histogram definitively, right? Because we have these boxes. Guys, we are rolling, and we've calculated outliers. I'm right now running through my slideshow to make sure I've hit every point with you, and we have done so well. And you're not even here. Well, you're here virtually, and I feel that energy and that magic, and I appreciate it. Oh my gosh. Mr. Mays may be out of language because we may have gotten everything that we want out of this set. Yeah, just remember with a box plot, we cannot be sure of anything except for left skewed, right skewed, right? Those kinds of things, and roughly symmetric. We cannot do approximately normal with a box plot. Be sure to do your AP question. That'll be super helpful. And then the last thing I want to be clear about is be sure you are exacting with your box plots versus your stem plots and whatnot. There will be often a comparison question. And what you'll need to say is whatever stem plot shows modality or shows, and actually you want to be specific. So don't just say modality. Shows that the distribution is whatever, bimodal or unimodal or even multi, if that's what it is, etc. Whereas, right, the box plot cannot. All right, we have managed to go through everything. So just to do my little scram up, I really like this like scroll. We talked about comparing different kinds of quantitative visualizations and stating what some do well and others do not do as well. Remember, stem plots don't put commas or points or dots or anything, and make sure that the leaf side has only one digit for each data point that you have. Don't skip bins or values. Start at the one that's most useful to your data set, but then from there, don't miss any. We then rolled up and took a look at box plots. We learned how to create a box plot in its totality. We also learned how to calculate the interquartile range. We learned the importance of the interquartile range because it holds 50%, count it, 50% of your data closest to your median. Right? We also learned how to calculate the outliers for that box plot. And we remembered to say to ourselves, we're going to check back and see if there's any data for that box plot that's present in a previous part of the question that we can use to determine the exact outliers when doing these calculations. Excuse me. We also learned that the median is super robust and that we should use it for situations where we have skew or where we have non-normal curves, because it will work well for us, and where we have outliers because we can cancel stuff out and it will work beautifully, right? We also learned that the box plot is kind of the perfect medium for using the median and the quartiles and things of that nature, and that's what makes it so gorgeous. We remembered how to calculate the median and also how to calculate the quartiles and what they mean, as well as the min and the max versus the outliers themselves. My goodness, it looks like art and graffiti we've created here. Remember that median and five-figure spread are your magic center measurements. Oh goodness, for when you need something robust. Center robusto. I feel like a coffee maker. Versus up here, we use mean and standard deviation when we need something gentler but more exacting. Stuff that is no skew and no outlier will do well with mean and standard deviation. We learned that standard deviation is something that holds the majority of our data, and that the further spread out your data points are, the higher your standard deviation will be, because you end up in a situation where your mean might be centered, right? But then you have to go really far out to pull in 68% of your data and call that one standard deviation from the mean. On the other hand, closely clustered data will have a low standard deviation, and that's the kind of thing that we like to see. We remember that there are two ways to talk about range. The range is blank. That's where you take your high and you subtract your low from it, or your maximum and subtract your minimum from it, and that's your finding your range value and say it. On the other hand, you could say the distribution ranges or varies from, and you'll say from high to low, right? And that will be your situation, or low to high. I recommend low to high. Minimum to maximum makes the most sense. Ranges from blank up to blank is normally how you want it. So I would say actually don't do max to min. That would make less sense. Okay. And I forgot to say, so I'm really glad we went through this. Remember that your standard deviation, it can equal 0, right? If all of your values are the same, so there's no variation from the mean. But it can never be a negative number. It's always a positive number. Oh, that was supposed to be our little beautiful thing, and instead it's hideous and gross and makes me hate myself, but that's okay, we're back on track. Positive is what that means, that's not a T. Beautiful. We stated that for histograms, we cannot calculate exact ranges, means, or medians. And I hope in this review you're like stopping and going like, yep, that makes sense, that makes sense, that makes sense, that makes sense. We talked about bins, that they're not exactly evenly distributed, so make sure you know that. But we can tell that, for example, standard deviations are greater or less than, which I said down here. We talked about calculating the median, I said that already. We talked about right skew, and left skew, and symmetrical distributions, right? Talking about box plots. We also talked about roughly uniform versus this is approximately normal. Both of those cannot be said of a box plot. Oh, goodness. Normal. Beautiful. We talked about clusters and gaps for shape. We also talked about unimodal, bimodal, and multimodal for shape. Median is the middle. Mean is the average, and we looked at skews for shape once again, and we talked about the ways in which the median versus the mean are distributed in different skews. The median is greater in left skews than the mean. The mean is greater than the median in right skews, and they are all the same for a normal curve, right? Remember to go back previously in data sets. Remember in compare, you do not need to use numbers. You can say this is greater than or less than this, but you have to compare all elements of the graph in CSOCs, and you have to compare all graphs. If I give you 3 graphs, you can't just compare 2 of the concepts in the graphs. Okay? In describe, you do have to use numbers. That's normally with one data set. Be sure to use things like about or around if you don't know an exact value so you don't get anything incorrect. We talked about CSOCs. We live by it. It is our Bible, our magic quantum realm. And this is for quantitative data. And I end up by reminding you these are the APFRQ tips that should make absolutely perfect sense to you and summarize the whole set. You've been brilliant. If you rewatch this video and in all its squalor and horrid sketchery and oddities and in my own odd pacing and windingness, it all makes sense because, mind you, these topics are very recursive. It's not going to feel linear. It's going to feel like we're mapping and folding on ourselves, like making a beautiful croissant of statistics. If it all makes sense to you and you can explain it to a toddler, and then you go back and you do the same with the first video lesson and the second video lesson, and you are ready for my mini quiz, be sure to check out the AP practice problem that I posted. You should be able to kill that. If you can kill it, you are also further ready for my mini quiz. Come and find me during office hours if you need anything, and I will further prepare you for your mini quiz. I appreciate you. You are a legend. You are in the best class I can possibly create, and I will keep trying to make it better. But remember, AP Statistics is the fabric of the world. It is the greatest topic we have the privilege to discover and to study because it is in everything, and I am the most privileged teacher because I get to work with you. Thank you. You've been a legend. This is Mr. Mays signing off.